Greetings everyone. In the previous lecture, we looked at the formation of a partial differential equation for an equation with arbitrary constants. We looked at different examples, and it is therefore important to note the following. The first one, if you have a case where the number of arbitrary constants that are to be eliminated is equal to the number of independent variables, then you will always have a PDE, or a partial differential equation of order 1. We looked at such examples, but for the purpose of understanding, we can consider one of the examples that we looked at. For example, we looked at an example where z was equal to ax plus by. You realize that we have two independent variables, that is x and y, and we have two arbitrary constants, that is a and b. So arbitrary constants, you have a and b, and independent variables, you have x and y. So you realize that the arbitrary constants to be eliminated, a and b, are equal to the number of independent variables, x and y. When you eliminate such arbitrary constants, then you will obtain a partial differential equation that is of order 1. So we need to take note of that, especially when you are dealing with the formation of a partial differential equation where you want to eliminate what we call the arbitrary constants. Then case number 2, if you have the number of arbitrary constants to be eliminated greater than the number of independent variables, then you will always obtain a partial differential equation that is of order that is greater than 1. For instance, if you consider like z, which is equal to ax plus by plus cxy. From this given expression, we note that we have got only two independent variables, that is x and y. But we have three arbitrary constants, that is a, b, and c. When you eliminate such arbitrary constants, you will get a partial differential equation that will be of order greater than 1. Then we shall look at the third scenario, that whenever you have the number of arbitrary constants to be eliminated, if they are less than the number of independent variables, then you will always have more than one partial differential equation. We can look at also an example. If, for example, you consider z, which is equal to ax plus y, you realize that you have two independent variables, that is x and y, but you only have one arbitrary constant. So It means that the number of arbitrary constants to be eliminated for this case is only 1, and the number of independent variables, they are 2. So the number of arbitrary constants to be eliminated are less than the number of independent variables. And for this case, when you eliminate this A, you will have more than one partial differential equation. Let us look at the formation of partial differential equation by eliminating arbitrary function. Here we shall be having two cases, and for our first case, we shall be considering when z is a function of u, but u is also a function of x, y, and z. But also z is a function of x and y. So we are having this scenario where f is a function in terms of u, but this u is also a function in terms of x, y, and z. And again, this z is a function of x and y. So that is the first case that we shall be looking at. But how best can we form a partial differential equation if we are having such a case? So we shall first of all let our z to be f of u, and as we have said, u is also a function in terms of x, y, and z. So if we differentiate, if we take partial derivative, we shall take partial derivative of z with respect to x. So this is our z equaling to f of u. So the partial derivative of z with respect to u will be same as differentiating this. So we are having del z, del x, which is same as, so we are differentiating f of u with respect to u, that is del f del u, then we shall multiply by del u del x. But we shall add there, because we know that z is also a function of x, because we have said z is in terms of u, but u is in terms of x, y, and z, of which also z is a function of x and y. So we shall as well add there del f del u, then times del u del z times del z del x. So meaning when we put f derivative of u outside the brackets, we realize that f derivative of u is common. So when we put f derivative of u outside the bracket, and we shall be having del z del x, which is equal to f derivative of u, then del u del x plus del u del z times del z del x. So that is when we pull out the f derivative of u. So this will be able to give us our equation number 1. Similarly, we can do the same when we take partial derivative of z equaling to f of u with respect to y. So doing the same for y, we shall be able to obtain del z del y, which is equal to f derivative of u del u del y plus del u del z times del z del y. And this will be able to give us our equation number 2. So when we look at the two equations, that is 1 and 2, we can easily eliminate f derivative of u by dividing the two equations. So when we divide the two equations, then we can easily eliminate f derivative of u. For example, when you get 1 divided by 2, you realize that this f derivative will cancel out, and you will possibly remain with partial derivative of z with respect to x, partial derivative of u with respect to x, the same partial derivative of z with respect to x. So you realize that the arbitrary function will be eliminated. So we shall look at all this when we come to examples, such that we are able to realize on how we can easily eliminate arbitrary functions. Let us now look at some few examples on how best we can form a partial differential equation by eliminating arbitrary functions. Let us begin with question number 1. Question number 1 says z is equal to f of x squared minus y squared. Our main task is to eliminate the function f. How do we do that? Let us look at the solution. We want to eliminate the arbitrary function f. So let us have u to be equal to x squared minus y squared. For this case, we can easily take the partial derivative of u with respect to x, which will give us 2x, and partial derivative of u with respect to y, which will give us negative 2y. So this will imply that our z will now be f of u. U is representing x squared minus y squared. So let us take partial derivative with respect to x of this expression here. So taking the partial derivative, that is differentiating with respect to x. So we are taking the partial derivative of this with respect to x. So we shall have del z del x, which is equal to, this is same as having del f del u times del u del x, which means you can still write this as f derivative of u times what is del u del x. Del u del x is 2x, so that is times 2x, meaning that del z del x is actually equal to f derivative of u times 2x. So we can call this one here as equation number 1. Next, we shall do the same for y, that is differentiating. We are differentiating with respect to y. We are differentiating z with respect to y. So differentiating z with respect to y, it means you will have del z del y, which is same as differentiating f with respect to u, then times del u del y, which will give us f derivative of u times del u del y. Del u del y, we have seen clearly that it is negative 2y. So this implies that del z del y is actually same as f derivative of u times negative 2y. We can as well call this one equation number 2. So we can easily notice that there is a relationship between equation 1 and equation 2. And if we want to eliminate this function here, then we can possibly either get equation 1, we divide it by equation 2, or we get equation 2, we divide it by equation 1. So let us get equation 2 and we divide it by equation number 1. We are having del z del y equaling to f derivative of u times negative 2y. But we are dividing the whole of this by del z del x, del z del x. This one here, we shall have f derivative of u times 2x. So from that is equation 2 divided by equation 1. We can easily notice that this function here and this will cancel out, and we shall try to cross multiply here. This will multiply with this, and this one will multiply by this. But similarly, we can also easily see that these two and these two will cancel out. And for that case, we have del z del y divided by del z del x, which is equal to negative y upon x, which we can easily rearrange to give us x times del z del y, which is equal to negative y times del z del x. And this will be x del z del y plus, when this one comes the other side, y del z del x. And this one here is equal to 0. We realize that the arbitrary function has been eliminated, and this will be our partial differential equation. Question number 2 says z is equal to f into x upon y. We need to form a partial differential equation by eliminating the arbitrary function. And we shall do this following the same steps as we have done in our question number 1. So let us look at the solution. We are having z as f of x upon y. We shall let u to be x upon y, which means from this u I can easily get the partial derivatives with respect to x and y of u. So let us have del u del x, and del u del x will be 1 upon y. Similarly, del u del y will be same as negative x upon y squared. So you are having, when you differentiate 1 upon y, this is same as differentiating y to power negative 1, and this will give you negative 1 upon y squared. But there is this x here, so that's why we have this. Now it implies that our z is same as f of u, which means del z del x will be same as having f derivative of u then times del u del x, which is actually same as having f derivative of u times del u del x, which is 1 upon y. Similarly, del z del y can be obtained as f derivative of u times del u del y. And this is actually same as having f derivative of u. Because we already have del u del y, we shall simply substitute it as negative x upon y squared, which is this one here. Now, we can let this to be our equation number 1 and let this one here to be our equation number 2. So from the two equations, that is from equations 1 and 2, from equations 1 and 2, we can easily divide these two equations here to eliminate f derivative of u. And that one will be same as having del. Let us get equation number 2. We divide it by equation number 1. So we shall have del z del y, which is equal to f derivative of u times negative x upon y squared. We are dividing this by del z del x. This one here is f derivative of u times 1 upon y. We shall have to eliminate this f derivative of u. It will be eliminated, and we shall now have del z del y. This one will multiply here to have 1 upon y del z del y, which is same as negative x upon y squared times del z del x, which we can easily simplify. So this y will reduce, and we can easily multiply this side by y to have y del z del y, which is equal to negative x del z del x. And finally, we can now have y del z del y plus x del z del x, which is equal to 0, as our partial differential equation, where the arbitrary function has been eliminated. We look at question number 3. Question number 3 says xyz is equal to f into x plus y plus z, and we want to form a partial differential equation majorly by eliminating the arbitrary function. So let us look at the solution. We are given xyz, which is equal to f into x plus y plus z. When we are starting this lecture, we looked at the expression that whenever we are given z, which is in form of f of u, for which this u is a function of x, y, and z is a function of x and y, then we looked at the partial derivatives of z with respect to x and the partial derivative of z with respect to y, as we said that del z del x is actually same as f derivative of u times del u del x plus del u del z times del z del x. We did the same for y. Where there is x, we simply had y. We shall now let u to be x plus y plus z, and for that case we can get del u del x, partial derivative of u with respect to x, which will be 1, partial derivative of u with respect to y, which will be 1, partial derivative of u with respect to z, which will be 1. So we want to take the partial derivative of this with respect to x first. Then also we do the same with respect to y. This implies that taking the partial derivative of this with respect to x, we shall have, first of all, we need to realize that x, y, z is in product form, because x, then z is a function of x and y, which means that x and z will be in product form. So we shall use product rule to apply on x, y, and z. And for that case, let us take x then and y, z as one function. So we shall maintain x, we differentiate yz with respect to x, and that will be y times del z del x. Plus, now maintain yz and differentiate x with respect to x, and that will give us 1. This will be equal to f derivative of u into del u del x. Del u del x is 1 plus del u del z. Del u del z is also 1 times del z del x. So we shall maintain del z del x, which means this will be xy del z del x plus yz, which is equal to f derivative of u into 1 plus del z del x. This is same as having xy p plus yz, which is equal to f derivative of u into 1 plus p. Remember that p represents del z del x. So we can further simplify this to have the common factor, which is y. So we can say p of x plus z into y is actually same as f derivative of u into 1 plus p. So we can call this one here as equation number 1. Next, let us do the same. Let us also differentiate the same expression with respect to y, following the same procedures. So it means y and z will be in product form, and we shall therefore use the product rule as we have done here. So looking at that, let us have xz as one function, then y as another function. For this case, let us maintain y, and we differentiate xz. When you differentiate xz with respect to y, you will maintain x, then you will have dz dy. Then plus, we maintained y and we differentiated x and z. We are taking partial derivatives, remember. Then we shall add there. Now we shall maintain xz, and we shall now differentiate y with respect to 1. Differentiate y with respect to y, and you will get 1. And this one will be equal to, we shall follow the same, that is f derivative of u into del u del y. Del u del y is 1 plus del u, here we are having this one, del u del z. So del u del z, what is del u del z, is also 1 times then del z del y, we are having del z del y. So that is what we shall have. This is same as having yx del z del y plus xz, which is equal to f derivative of u into 1 plus del z del y. So that is what we shall have, but still we can simplify this one further. Where there is del z, del y, we shall simply put a q. Remember, q represents del z, del y. And this one will give us, clearly, we have x yq plus xz, which is equal to f derivative of u into 1 plus q. That is after substituting for q where there is del z, del y. Then here also where there is del z, del y, we have placed q. So that's why we have this given expression here. But from that same expression, we can easily factorize out x, since it is common here, such that we have yq plus z into x, which is same as f derivative of u into 1 plus q, and we can call this one here equation star. We need to recall that our equation 1 was given as px plus z into y, which is equal to f derivative of u into 1 plus p. That was our equation number 1, which is here px plus z into y, which is equal to f derivative of u into 1 plus p. So from the two equations, equation star and equation 1, we can easily eliminate the arbitrary function, that is f derivative of u. So we shall say from equations 1 and star, we can easily eliminate the arbitrary function by simply dividing the two equations. So let us get equation 2, we divide by equation 1. So we shall have, so we are considering star, so that is equation star divided by equation 1. So we shall have yq plus z into x is equal to f derivative of u into 1 plus q. This is divided by p of x plus z into y divided by f derivative of u into 1 plus p. So we shall cancel out this such that we remain with, this will imply that if I cross multiply this one here, I will have yq plus z into x times 1 plus p, but this is same as having p of x plus z into y times 1 plus q. So we can try to simplify this expression here. We can try to simplify this expression. So we shall multiply this x here such that we have yq plus z into x plus p of x, which is same as having also p of x plus z into y plus yq. Similarly, we can now open these brackets such that we have x y of q plus x y of pq. We have multiplied this with this one with this. Then z, that is xz plus xzp, and this will be equal to, we do the same, that will be xyp plus this one multiplied here will give us x, y, p and q plus zy plus y z of q. So we can now easily relate these two, because we are equating. This one is equal to this, so we realize that this one and this one is common, so it will cancel out, and we shall simply remain with xyq, xz, xzp, xyp, zy, and yzq. So let us try to bring all these terms here on our left hand side. So we shall have xyq. I will also subtract the expression containing q, that is minus yzq, plus this is xz. I will subtract zy, plus this is xzp. We shall also subtract x. We shall also subtract xyp, and this should give us a 0. So we shall try to collect some of the rest. We shall try to factorize. So here we realize that yq is common, so it means we can say y into this will remain as x minus z into q, plus we realize that z is common here, that will be x minus y into z, plus this is xzp, this is xyp. So we realize that xp is common, so we shall have plus, let us put x out and p, so we shall remain with z minus y into p, and this will be equal to 0. So this one here will become our answer. So you realize that within this expression we have totally eliminated the arbitrary function, which is f, and this will become your answer. So thank you for watching. Please, if you find this video helpful, don't forget to subscribe, share, and like. Thank you, and have a blessed day. Yeah.